Hi everyone, this is an introduction to digital electronics. So before you watch this video and any of the following videos, do make sure that you understand binary numbers. Binary numbers are very used in this course, so it'll be in this module, so it'll be needed that you study binary numbers. Very simple concept really. So in this circuit that we are looking at right now, which one is the input and which one is the output? So you know when you on a light, that's your input because you're inputting the turning on the light, and the output is the light because when you turn it on, the light will turn on, and when you switch the light off, when you switch the switch off, you turn the light off. So this is your input, and this over here is your output. You see by the arrows over here, going in for the input and then going out for the output. So knowing this, we can say that when it is high, so when high, we consider this to be logic 1. And it becomes more obvious what this means when we look more into it. And when it is low, when low meaning it's not on, we call it logic 0. So let's say input equals 0, meaning the switch is now open. The output will also equal 0 because the light is off. Now let's say if I close this, so you can see by the green, if I closed it, meaning input equals 1, the light will turn on, and this means the output equals 1. So what we can say, because now we have it in zeros and ones, is that input equals output. And this is the basis of Boolean algebra that we'll be looking at. So if we call the input A and the output to be X, we can say that A equals X. Because you know when A equals 0, so just an example, when A equals 0, then X equals 0. When A equals 1, X equals 1. So it's very simple, very obvious like that. Basic algebra, basic Boolean algebra. So now we'll be looking at this circuit, and this is called the NOT gate. So we will want to analyze the same thing that we did before. So now I've put in something called the truth table. The truth table is essentially checking the truth of the circuit. So checking the truth of the circuit. So the truth of this circuit was A equals X. This was the truth of this circuit, the equation of this circuit. The truth of the circuit meaning what is true about this circuit, and we can check it through the truth table. So let's say in this circuit we first put our input. Let's say A equals 0. So now A is your switch. A equals 0. What will happen? A equals 0 when the switch is off. So we'll just follow a current. The current will go from the VCC, the power meaning the power, and then it will go down, go through the light bulb, and then it will go down to the ground. So as you can see, X equals 1 because the light bulb will be turned on, so it will be in logic high. Understand? Now let's say we close the switch. So let me just get a new color. Let's say we close the switch. So when A equals 1 basically. So now the A equals 1, meaning the switch is on. So we can represent it by the blue line over there. The switch is on. I should actually just cut off the line, but you know, I don't think there's a need to. So, oh, I forgot this. So the output equals to 1. So just now, you know, it turned on. So now it goes switch. Now you go to the path of 0 resistance. You know, if you should know this. You go the path of 0 resistance, skip the light bulb, just draw current, meaning the light bulb won't be turned on. So 0. So this is much different. This was much different from the previous circuit, and this is why it is called a NOT gate. Essentially, the equation of this is A equals not X. And this can also be represented by A equals X bar, or A equals x, comma. I mean, a comma, apostrophe. But the one that is commonly used is a equals x bar. Or I mean, just bar in general. So can prove this with when a equals 0, it will equals to 1 bar, and what's not 1, it is 0. So 0 equals 0. And when 1 equals 0 bar, what is not 0? It's 1. Because what's high, what's not high, it's low. What's not low, it's high. So we'll only be looking at zeros, ones opposite of each others. And we'll only be looking at the possible number of combinations for the circuit. So if you realize over here, there's no other different way we can play around the circuit. It's either you on the switch or you off it. There's no other way. So 1, 0. And how we can represent this, how we can represent what we just did, is with this gate over here. So essentially, what this thing over here is this portion of the circuit. The green portion is this portion. So we can just put a VCC. So we can just put A. So this was our input, and then this was our output. So we can put output. We don't even need to put the light bulb because we know that the light bulb is the output X over here. This is the equivalent of what we just did. It can be represented with a gate. So we call this a gate. This symbol is called a gate. Very important, and very important to know that this bubble over here, this bubble, is what represents the NOT. So in the next two gates that we'll be looking at, we won't be seeing this bubble, but in following circuits and following gates, we will be seeing this bubble. So remember, what represents NOT is this bubble. So if there's a current going in, bubble, no more. So just note that these circuits are actually a bit inaccurate because you shouldn't be looking at it as a current. But to understand the gates, I think it's best to look at it this way. Okay. Next, the AND gate. So now you can see that we have two different inputs and we have 4 different combinations. And how this can be determined is by using basic binary numbers. So if you know binary numbers, we'll go 0, 0, 0, 1, 1, 0, 1, 1. So you can see there's no other combination. And to guess how many combinations there are, we just have to do 2. So that's base of binary numbers, and the number to the power of number inputs. So this is to find the number of different combinations. So 2 to the power of 2, 4. That's the number of combinations we have, and that's the combination shown here, 4. So now we'll be evaluating this truth table and seeing why it is called the AND gate. So firstly, 0, 0, that's clear cut. X is going to be off. So 0, 0, no current is going to pass. Current is just going to go like that, right? Now let's close B. So let's say we closed B. Let's say we close B. No current is going to pass. So we get that. No current is going to pass. 0. Now let's say we close A. We close A. No current is going to pass. So pretty clear. There's going to be a 0. Alright? Oops. That's a bit much. Now, if I close A and B, so I closed A and B, I closed A and B, now a current is able to go straight down, turn on the light bulb, and X is finally 1. So as you can see, we need to switch on A and B for the circuit to be on, and that's why it's called the AND gate. And this can be represented with this: A, B, and X. And it should be noted that for multiple input gates like the AND gate, it is possible to have 3 inputs. It's possible to have things like a 3 input gate, A, B, C, as long as there's one output for each gate. But there can be 3 inputs, and to on this 3 input gate, you will need all of it to be logic 1 high. Okay, and the equation for an AND gate, so let's just a note for later on. the equation for basic AND gate for 2 input AND gate would be x equals, it's better to have the output at the left, the input at the left. A times B, so that's A times B equals x. Or you can have AB equals x, A, B equals x. They're all the same thing, it's just simple math. It's just same as your basic algebra math. So A times B equals the input. And this times represents an AND. Oops, AND. This times represent an AND. So to get x to equals 1, you need A and B to be high too. So that's represented by this truth table, and this truth table proves it. The last one, you guess it, if there's an AND, there's probably an OR. So we do our guessing. So we know that there's 4 inputs because there's 4 different combinations. Combination inputs are different thing. So 4 different combinations and 2 different inputs. So there's 4 different combinations, 2 different inputs. Now we will check. If 0, 0, the current will only go like that. So x will of course equal 0. But now, when b equals 1, we will see that the current can go through here and turn on the light bulb. Knowing that, you know that equals 1. Now, when A equals 1, we check when A equals 1, the current will go down and also get the light bulb. So equals 1. And when we turn both on, it's still possible for the current to split, get to this junction, so Kirchhoff's law, but doesn't really matter, and boom, 1, 1, 1. And what we do notice is that for x to be high, meaning 1, we only need either A or B or AND to get x to be high. So we can represent this with a curved line. So make sure there's a curve, and A, B, x. And it's same as the AND gate. If there's multiple this is a multiple input gate. So A, B, C, this is still possible. And to represent the equation for this circuit would be A plus B equals to x. Alright. So just simple Boolean algebra. So if you want to evaluate just now circuit, it'd be A times B. So let's just take the first and last combination. The second and third combination. So 0 times 1 will equals to 0. And then 1 times 1 will equals to 1. So this is for the AND gate. And for the OR gate, I keep thinking of different gates. 0 plus 1 will equals to 1. 1 plus 1 will equals to 1. And that's it for basic gates, and that's all you have to understand. Hope this was a good introduction, and we'll be looking at the universal gates and even more in future videos.